So the product rule. So let's let f of x be the product of two other functions of x, u and a v. And if we apply the principle of differentiation from first principles to find out how we can come up with a formula to differentiate a product. So then f dash of x derivative will equal the limit as h tends to 0 of u of x plus h times v of x plus h, take away u of x, v of x all over h. Now it's not very clear what we can do with that. However, we're going to rewrite the numerator to see if this can help us. Okay, so what we've done there, we've kept it equal by adding and taking away the same term. So we've took away u of x times v of x plus h, then added it back on again. So actually when you simplify it, it's no different to the line above. However, we now have four terms and we can look at factorising the front two and the second two. Now does this start to look familiar? Let's split up the two sums on top of the fraction. We'll have two separate fractions, both over h. Okay, so we can see that in those two brackets, we've got v of x plus h times u of x plus h minus u of x over h, and plus u of x multiplied by v of x plus h minus v of x all over h. Those two expressions in the brackets are the definitions of the derivative of u and derivative of v from first principles. So as h tends to 0, we will get the following. We will get v times u dash plus u times v dash. In other words, or we could say v du dx plus u dv dx. So we take both terms in the product, we differentiate both of them, and they sub them back into that expression. We'll see an example now. Okay, example. Got f of x is equal to 3x plus 5 all cubed multiplied by x squared plus 1 to the power of 4. So if we split into our product of two terms, we've got u is 3x plus 5 cubed and v is x squared plus 1 to the power of 4. Now we just need to differentiate both of them. Okay, so u dash will be 9 lots of 3x plus 5 all squared, and v dash will be 8x multiplied by x squared plus 1 cubed. Okay, so f dash of x is uv dash plus v u dash. This is a perfectly acceptable answer. It is an expression for the gradient function of the f of x. However, it doesn't look very neat, and it would be nice if we could neaten it all up so we'd be able to find any stationary points where possible. So we can factorise this expression. We can see that in both cases we've got a 3x plus 5 and the lower power is squared, and we've also got an x squared plus 1, which again the lower power this time is cubed. So we take those two out as a factor, we can see what the rest of it will simplify to. So taking those two terms out, inside the square bracket we have 8x lots of 3x plus 5 plus 9 lots of x squared plus 1. Now we can, as you can probably see here, we're going to get a quadratic expression inside that bracket. So we could find there whether that one factorises further, or we just have to leave it as the quadratic. And there's our final expression. X squared plus 1 all cubed times 3x plus 5 all squared times 33x squared plus 40x plus 9. Sadly that quadratic does not factorise to make that better, but however that is the expression for the gradient, and from that we could find where the gradient is 0 and then work out whether or not they are maximum or minimum. The quotient rule is where we want to differentiate quotients. So we split our more complicated function into one function over another, in this case u of x over v of x. And we're going to apply differentiation first principles again to see whether we can find the rule. So this will give us the limit as h tends to 0 of u of x plus h over v of x plus h, take away u of x over v of x, all over h. When we divide by h, it's the same as multiplying by 1 over h. So if we get this into a single fraction, where the common denominator will be h, v of x times v of x plus h. Again, with this, we're going to add and subtract something to the numerator to keep it equivalent. However, then we could factorise the first two terms and the second two terms. So we took away u times v and added u times v to keep it all the same. But notice now the first two terms have v of x common, and the second two terms have a u of x common. So we take out those factors, or the first two and the second two, and we should hopefully get something that resembles our differentiation from first principles definition. With the numerator and the second set pair of terms, I take a minus u of x, so that inside my bracket I could have v of x plus h, take away v of x. So both of them match. They're both can be put over h, which links in with the differentiation first principle definition. Now by rewriting this, we can see we've got the definition of u dash and v dash in there. We've also got v over v of x times v of x plus h. We've also got u over v of x times v of x plus h. Now as h gets smaller or close to 0, those numbers and terms at the bottom comes to v squared. So this will give us an overall formula of, we have v times u dash, take away u times v dash, all over v squared. So for example, we have f of x is x squared plus 3 over 4x plus 1. And then we let u equal x squared plus 3 and v equal 4x plus 1. So u dash becomes 2x and v dash becomes 4. So f dash of x is equal to vu dash minus uv dash all over v squared. So plugging them into the formula like that, we have 2x, lots of 4x plus 1, take away 4, lots of x squared plus 3, all over 4x plus 1, all squared. Now time to tidy up the top, simplify it, and leave it as a single fraction. Our numerator now becomes 8x squared plus 2x minus 4x squared minus 12. Be careful with your negative signs. This, of course, simplifies to 4x squared plus 2x minus 12, which we can factorise further. We take out a factor of 2, and you can also see that the actual quadratic factorises to get us 2 lots of 2x minus 3 times x plus 2 all over 4x plus 1 all squared. So you can see from that it has two stationary points when x is minus 2 and when x is 1.5.